Do something small for me before we start. Put your hand near whatever device you're listening on, the phone, the laptop, the little speaker in the corner, and notice that it's warm. We all know why, or we think we do. It's working, so it heats up, the way anything working heats up. But here's the thing I want to sit you down with tonight. Part of that warmth isn't from the thinking at all, it's from the forgetting. Every time that machine clears a scrap of memory, throws away a number it's finished with, wipes a slot clean to reuse it, it warms the air around it by a tiny, exact, unavoidable amount. It cannot forget for free, and it turns out nothing in the universe can. Hiding inside that one strange fact, that forgetting has a temperature, is a secret about what information actually is, not a metaphor, not abstract mathematics floating off somewhere. A physical thing with a real price woven right into the laws that run the world.
That's the right place to start the whole journey, and I'm glad you put your hand on the warm patch first, because most people go their entire lives feeling that warmth and never once asking the strange question hiding in it. They assume the heat is the cost of the work, of the machine grinding away, doing sums. And that's the half of it that's wrong. The deep, beautiful, slightly unsettling truth is that a machine can, in principle, think as hard as it likes for almost no cost at all. What it can never do for free is forget.
All right, that's already got its hooks in me because that's backwards from everything I'd have guessed. Forgetting feels like the easy thing. Forgetting feels like doing nothing. You just let go. How is letting go the expensive part?
That's exactly the knot we're going to spend tonight untying. And by the end, I want you to feel why it has to be that way, not just take my word for it. But we can't even ask the question properly yet, because we've been throwing around a word as if we all know what it means. Information. You said it, I said it. Before we can talk about what information costs, we have to be honest about what information is. And someone had to figure that out. It wasn't always a thing you could measure. The atom of information.
I'll bite. What is information? Because to me it's words, pictures, the news, a song. It's stuff that means something. That doesn't sound like a thing you'd put on a scale.
And that instinct, that information is about meaning, is the very thing the man who cracked this had to throw away to get anywhere. This is back in the late 1940s, a quiet engineer at a telephone company, wrestling with a dull-sounding problem. How do you send messages down a wire cleanly, and how much can you cram down it? His name was Claude Shannon, and what he did was one of the great acts of letting go in the history of science. He said, "Forget meaning. A love letter and a page of pure gibberish, if they're the same length, can carry the very same amount of information. Meaning is not the point. The point is choice." How many possibilities did this message pick out from?
Hold on. You're telling me a love letter and total nonsense are equal. That feels almost offensive. One of them matters and one is garbage.
One of them matters to you. But the wire doesn't care, and the mathematics doesn't care. And that not caring is precisely what lets Shannon turn a fuzzy human word into something you can actually count. Let me show you the counting with a game you already know. 20 questions. I'm thinking of something, and you can only ask me things I answer yes or no. How do you play it well?
You don't waste questions. You don't ask, is it a badger, straight off. You ask something that splits the world roughly in half. Is it alive? So that whichever way I answer, you've knocked out about half of everything.
You've just described the whole of information theory in one breath. Each really good yes or no question cuts the field of possibilities in half. And that single act, a clean cut of the possibilities into two and being told which half, that is the atom. That is the smallest indivisible drop of information there is. Shannon gave it a name that's now so common we forget it was ever coined. He called it a bit. 1 bit is the answer to one perfect yes or no question. 1 halving, 1 fork in the road, and word of which way it went.
So a bit isn't the thing, it's the choosing between two things, the heads or tails of it.
The heads or tails of it, exactly. Picture a coin that's already been flipped and slapped down under a hand, and you haven't seen it. There's a fact there, heads or tails, that you don't have. The instant the hand lifts and you see it, you've received precisely 1 bit. Your uncertainty went from 2 possibilities down to 1 settled fact. That's it. That's a bit delivered.
And if it's a rolled die under there instead of a coin?
Then there's more to learn, so it's more than 1 bit. Because knocking 6 possibilities down to 1 takes more halvings than knocking 2 down to 1. And here's the lovely, slightly ruthless part. Information measured this way is really a measure of surprise. If I lean over and tell you the sun came up this morning, I've handed you almost nothing. You were never in doubt, there was no fork, nothing got halved. But if I tell you something you genuinely couldn't have guessed, something with a lot of live possibilities in it, I've handed you a great deal. Information is the amount by which your uncertainty shrinks. No uncertainty to begin with, no information in the telling.
That's a strange inversion though, isn't it? The more predictable a message is, the less it's actually carrying. So a machine that just prints the letter A over and over forever is saying almost nothing, no matter how much paper it uses.
Almost nothing. You've got it precisely. All that paper, barely a whisper of real information, because after the first few you're never once surprised. And this is the move that changed the world quietly and completely. Once you can count information in bits, in clean, countable halvings, you can measure it, store it, price it, push it down a wire, and know exactly how much you're pushing. Every digital thing you have ever touched, every photo and song and message is a pile of these bits, these settled coin flips, stacked up. Shannon gave us the atom, and for a while that's where the story sat. Information as a beautiful bookkeeping, a mathematics of messages. Elegant and seemingly weightless, seemingly free.
Seemingly? You keep leaning on that word like it's about to give way.
It's about to give way. The asymmetry nobody expected.
So walk me off the cliff. Where does a bit, a thing that's just a halving, a yes or no, where does it get a weight in the physical world? A coin flip doesn't warm the room.
The coin flip doesn't. But watch what happens when we ask a very practical question, the kind an engineer at a computer company would ask. This is the early 1960s now, a man named Rolf Landauer, and his question was blunt. When a computer does its work, when it churns through its bits, does it have to use energy? Is there some flaw, some unavoidable minimum below which no machine can ever go, no matter how cleverly you build it?
And I'd have assumed, obviously, yes, everything costs energy. There's no free lunch, the second law of thermodynamics and all that. Machines run hot. That's just life.
That's what everyone assumed. And Landau found something far stranger and far more particular. He found that most of what a computer does, the actual reckoning, the logic, the shuffling of bits from here to there, carries, in principle, no unavoidable cost at all. You could imagine doing it as gently as you like, using less and less energy, with no flaw, right down toward nothing. But, and here's where the ground opens, there's one specific act that is not free. One operation that carries an iron unavoidable price no cleverness can dodge. And it's not calculating, it's erasing. Wiping a bit, resetting a slot in memory to blank, no matter what was in it before. That and that alone has a minimum cost. Always, everywhere.
Okay, that is genuinely bizarre. Say it back to me plainly because I want to make sure I'm hearing it. Doing the sum, free or as good as. Rubbing out the answer afterward, that's the part you have to pay for.
That is exactly, precisely it. And the moment you really hear it, it sounds insane. So let me make you feel why. because Landauer didn't just assert it. There's a reason baked right into what erasing is. Come to a whiteboard with me. Imagine a single little box drawn on it, a slot, and in that slot lives one bit. It's showing either a 0 or a 1. Now, I want you to erase it. Not set it to whatever it already was, truly erase it, which for a machine means force it to a known blank, force it to 0, whatever it was holding before.
Right, so if it was a 1, I flip it to 0. If it was already 0, I leave it. Either way, afterward, it's 0.
Afterward, it's 0. Always 0. Now here's the fork you just walked through without noticing. Before the erase, there were two different situations in the world. The slot might have been holding a 1 or holding a 0. Two possibilities. Two roads in. And after the erase, there is exactly one situation. It's 0. One road out. Tell me, from the 0 you're left holding, can you say which of the two you started from?
No, that's gone. Once it's blank, blank is blank. I've got no way to know whether it used to be a 1 or a 0. The before is unrecoverable.
You've just put your finger on the whole thing. Erasing takes two possible pasts and funnels them into one present. And in doing so, it destroys the difference between them forever. It is a road you cannot walk backwards. And nature, it turns out, keeps a very strict ledger about roads you cannot walk backwards. Why forgetting has a temperature.
See, this is the leap I still can't feel in my gut. I follow that erasing loses track of the past. Logically fine, 2 into 1, can't undo it. But that's a fact about logic, about information. How does a fact about logic reach out and warm up the air? Where does the actual heat come from?
This is the deepest turn in the whole episode, so let's take it slowly and really earn it. The bridge between the two, between you lost track of a possibility and the room got warmer, is a word you've met before, probably as a vague menace. Entropy. Most people are told entropy is disorder or the universe running down, and they nod and move on. But underneath, entropy is something much sharper and much more countable. Entropy is a measure of how many possibilities are in play, how many different specific states a thing could secretly be in, while looking the same to you from the outside.
Possibilities again. That's the same currency as the bit, the coin that could be heads or tails.
It is the very same currency. And that is the secret handshake at the heart of tonight, the thing that took people a long time to see. The entropy the engineers were counting in messages, in bits, in halvings, and the entropy the physicists were counting in steam engines and hot gas a whole century earlier, without any thought of information at all, are not two cousins that happen to share a name. They are the same quantity. Counting the possibilities in a message and counting the possibilities in a puff of gas is the same act of counting. And the deepest law we have about that count, the second law of thermodynamics, says the total number of possibilities in the world, tallied all up, can never quietly decrease. It can hold steady, it can grow. It can't shrink for free.
Oh, wait. So when I erase that bit, when I take two possibilities and crush them into one, I have just made the possibilities shrink. The slot went from could be two things to is one thing. I've reduced the count. And the second law says I'm not allowed to do that for free.
There it is. You just built Landauer's principle with your own hands. You reduced the possibilities in your little slot of memory. You paid down its entropy, tidied it, forced it to a known blank. But the total across the whole world isn't allowed to drop. So that missing entropy, that lost handful of possibility, doesn't vanish. It gets pushed out, shoved into the air around the machine, into the jostling of the molecules, as the one form entropy takes when it's out loose in the world. Heat. The possibilities you squeezed out of the memory reappear as warmth in the room. They have to go somewhere, and heat is where they go.
So the warmth isn't a side effect of erasing. The warmth quite literally is the erasing. It's the possibilities I deleted from the memory, showing back up as jiggle in the air.
That is as clean as anyone has ever said it. And there's a definite flaw to how little that costs. The smallest possible puff of heat you must dump to erase a single bit. It's a specific number, Boltzmann's constant times the temperature times the natural logarithm of 2. You don't need the formula. You need 3 things from it. 1. It's never 0. You always pay something. 2. It's fantastically, ludicrously small. For 1 bit, a speck of heat so tiny you could never feel a single one, not with the finest instrument you own. And 3. It gets bigger when it's hotter. The price of forgetting goes up with the temperature, which is about the most physical thing a supposedly abstract idea could possibly do.
And a real machine isn't erasing 1 bit, it's erasing
Trillions. Trillions of them, every single second, all day long. Overwriting, clearing, resetting, throwing away intermediate scratch work the instant it's done with it. Each erasure, a speck of heat far too small to notice. Pile up enough of the uncountable specks, though, and you get exactly the warm patch under your hand that we started with tonight. Your device is not, mostly, sweating from the effort of thinking. It is sweating from the relentless, ceaseless labor of forgetting, of clearing room to think the next thought. That warmth is the sound of the ledger being paid, 1 trillion times a second.
That's going to change how I feel about a fan whirring in a laptop. That's the machine forgetting, out loud.
That's the machine forgetting, out loud. Hold on to that image. A warm computer as a machine paying, over and over, the tax on forgetting. Because we're about to meet a creature who tried to cheat that very tax, and very nearly broke the deepest law in physics doing it. The demon at the trapdoor.
A creature. You're going to tell me a ghost story.
I'm going to tell you the most famous ghost story in all of physics, and it haunted the field for the better part of 100 years. It comes from one of the greatest physicists who ever lived, James Clerk Maxwell, back in the 1800s. Maxwell believed in the second law completely. This rule that the world's possibilities, its entropy, only ever climb. That heat flows from hot to cold and never the tidy way round. That you can't build an engine that runs forever on nothing. But being a great scientist, he wanted to poke it, so he dreamed up a little imp, later people called it a demon, to try and beat it.
Set the scene for me. What's the demon do?
Picture a sealed box of air, split down the middle by a wall, and in that wall, a tiny trapdoor. The air in there is the usual roiling crowd of molecules, some flying fast, some drifting slow, all mixed together evenly, both sides the same warmth. Now put our demon at the trapdoor and give it sharp little eyes and a quick little hand. It watches the molecules come at the door. When a fast one comes flying from the right, it flicks the door open, lets it through to the left, snaps it shut. When a slow one drifts up from the left, it lets that one through to the right. Fast ones it herds to one side, slow ones to the other. Patiently. For a long, long time.
And fast molecules are hot, and slow molecules are cold. That's basically what temperature is, how fast the little things are jiggling. So, after a while, the
demon has sorted them. One side of the box has filled up with the fast movers and grown hot. The other side has filled with slow ones and gone cold. It started evenly warm all over, and now, purely by the demon's patient sorting, there's a hot half and a cold half.
And a hot side next to a cold side is exactly what an engine wants. That's a difference you can run a machine off. Heat flows from hot to cold, and you catch some of it as work on the way. So the demon has manufactured an engine's fuel out of thin air. Out of nothing but watching and sorting.
Out of nothing but watching and sorting. It did no pushing, no shoving, no work in the ordinary sense. It just decided which molecule goes where, and it created a temperature difference from a uniform box, which means it made the world's entropy go down, for free, which the second law flatly forbids. And you could run that engine, let the box even out again, then let the demon re-sort it, and run it again. Forever. Free work, out of a sealed box, with no fuel, on and on with no end.
Which is impossible. That's a perpetual motion machine. Everything in me says that can't be real.
Everything and everyone said that. And yet, nobody could say precisely where the demon cheated. That was the scandal. The logic looked airtight. There's the box, there's the door, there's a clever little sorter, breaking the most trusted law in all of physics, and for decade after decade, the finest minds in the world could not put their finger on the flaw. The demon just sat there at its trap door, grinning, sorting, and getting away with it.
So where's the catch? Because you've clearly got one up your sleeve, and I've been trained by now to expect it's not where I'm looking.
It's never where you're looking. But before I give you the catch, let me do what a young physicist did in the 1920s. Let me strip the demon's game right down to its bones, until there's nothing left to hide behind. Because the fully dressed demon, with its whole roaring crowd of molecules, is too busy to think about clearly. We want the demon reduced to the single simplest bet it ever makes. One molecule, one bit.
Strip it down how far?
All the way down to one molecule. This is a Hungarian physicist, Leo Szilard, and his move was gorgeous in its severity. Throw out the crowd, put a single molecule in the box, rattling around, banging off the walls. Just one. And now play the demon's game with that.
One molecule in a whole box. Okay, what can a demon even do with one?
Watch. The demon looks, just once, and asks the box one question. Which half is the molecule in right now, the left or the right? That's the entire observation. One question, two possible answers. Left or right?
That's a bit. That's one clean yes or no. Left or right is heads or tails. The demon has learned exactly one bit about the molecule.
Exactly one bit. Hold that, because it's the hinge of the whole thing. Now watch what the demon does with that one bit. Say it learns the molecule is on the left. So the right half is empty. The demon knows this. It slides a piston in from the right into the empty space. No resistance, costs nothing, because there's nothing over there to push against. And now it lets the molecule do its thing. The molecule keeps rattling around, and every so often it slams into the face of the piston and shoves it a little toward the right.
So the one molecule is slowly pushing the piston back over, battering it one hit at a time, expanding into the whole box again.
And if you hook that piston to a tiny lever, a thread, a weight, the moving piston lifts the weight. Real work, genuine, cash-in-hand, lift-a-weight work, harvested from a single molecule in a box. And when the molecule has pushed the piston all the way across and filled the box again, you're back exactly where you started. One molecule rattling in a full box, ready to go again.
Wait, let me make sure I've got the size of this. The demon looked once, it learned one bit, just left. And it turned that one bit of pure knowing into an actual pull on an actual weight. It converted information into work.
Information into work. A precise, countable amount of it. And here is the detail that should make the hair stand up on your arm. The work you can squeeze out of that one bit of knowledge comes to exactly Boltzmann's constant times the temperature times the natural logarithm of 2.
That's the number, that's the same number, that's Landauer's flaw, the cost of erasing one bit. You just told me the work you get out of one bit is the identical amount as the price of wiping one bit.
The very same. to the last decimal. And that is not a coincidence. That is the universe showing you its hand. But hold the excitement one moment, because right now, on the face of it, Szilard has made the scandal worse, not better. He's stripped the demon down to one molecule, and it still works. One bit in, real work out, reset, go again, forever. Free energy from a sealed box, and now we can even name the fuel it's supposedly running on. The fuel is information, the demon's knowledge. And that seems to say knowledge is a free, bottomless well of energy, which is madness. So, where is the catch? You've earned it now, where the bill comes due.
All right, my instinct says it's got to be in the looking. Surely the demon can't just see which side the molecule's on for nothing. It has to shine a light on it, or bounce something off it, or somehow reach out and check. And that costs. That's where the energy sneaks back in, right?
That is exactly where nearly everyone put it, for the longest time, including some brilliant people who worked hard to prove that the act of measurement, the looking, must cost at least as much as you gain. It's the natural guess. It feels right. Looking should cost. And it turns out, it doesn't have to. That's the twist. People eventually showed that you can, in principle, make that measurement as gently as you like. You can look for almost nothing. The looking is not where the debt is hiding. The demon really can find out which side the molecule is on, essentially for free.
Then I'm stuck. If the looking is free, and the molecule does the pushing for free, and the piston slides in for free, where on earth is the bill? The books have to balance. You keep telling me the second law always wins. So what did I miss?
Think about what the demon is holding at the end of one round. Go back to the moment it looked. It learned a bit. Left. Where does that bit live, now, between looking and acting? It lives in the demon, in its head, in its notebook, wherever a demon keeps things. The demon has a memory, and after one round, that memory is no longer blank. It's got a bit written in it. The molecule was on the left.
And to go again. To run the next round cleanly the same way, from the same fresh start, the demon needs its memory blank again. It has to clear that bit out. It has to...
Say it.
It has to erase. Oh, that's... The demon has to forget. Before it can play again, it has to wipe left out of its memory. And erasing one bit costs...
Boltzmann's constant, times the temperature, times the natural logarithm of 2. The exact amount of work it just extracted. Every round, the demon squeezes that much work out of the molecule, and then, to reset and go again, it must pay that very same amount back, as the unavoidable heat of erasing the one bit it wrote down. The work you win at the piston, you lose at the wipe. The books balance to the penny, and they balance at the one step you and I would never have thought to look at. Not the clever sorting, not the looking, not the pushing. The forgetting, the tidying up, the clearing of the notebook to make room for next time.
So the demon never actually beat the second law. It was running a tab. It could win round after round, as long as it had blank memory to write new bits into. It's borrowing against its own empty pages.
That is the most beautiful way to see it, and it's exactly right. As long as the demon has fresh, blank memory, it genuinely gets free work. It really does cheat for a while. It's not a trick or a lie. The work is real. It's a loan. It's borrowing against empty pages. But the pages are finite. Sooner or later, the notebook is full, and to keep playing, the demon must erase. And the instant it erases, the whole loan comes due, every last bit of it, repaid as heat, with interest that can never be less than what it took. Over any complete cycle, where the demon ends as blank as it began and can truly go again, the second law stands perfectly, untouched. The demon didn't break it. The demon just showed us the one loose thread, And following that thread, we found that the law is held together, in the end, by the cost of erasing information.
I need to say the shape of that out loud, because it's enormous. The second law of thermodynamics, the most trusted, most unbreakable law we've got, the one that says the arrow of time only points one way. And you're telling me the thing standing guard over it, the thing that stops the demon, the thing that makes the whole ledger balance, is a fact about erasing bits, about forgetting. The law of heat is protected by a truth about information.
The law of heat is protected by a truth about information. And that is the same truth we started the whole evening with, standing over the warm patch on your machine. The demon and your laptop they're the same story, told twice. Neither one pays to think, neither one pays to look. Both of them pay in heat, in warmth shed to the world, for exactly one thing: to forget. Your laptop is a demon at a trapdoor, sorting bits all day and paying its tab 1,000,000,000,000 times a second in the warmth under your hand. Information is physical.
So this is what you meant all the way back at the top, when you said information isn't abstract math floating off somewhere. It's in here. It's in the thermodynamics. It's in the same ledger as heat and engines and the arrow of time.
It's in the same ledger. That's the whole payoff of tonight, and it deserves to be said as plainly as I can say it. For a long time, people carried two separate pictures in two separate pockets. In one pocket, physics, real stuff, matter and energy and heat, things with weight, things you could measure and price. And in the other pocket, information, messages, bits, logic, a kind of ghostly, abstract bookkeeping that floated above the physical world and never quite touched it. And what this whole story shows, Shannon's bit, Landauer's flaw, Maxwell's demon, Szilard's molecule, the debt that comes due at erasure, is that those two pockets were always one pocket. Information has a temperature. A bit has a price, paid in heat. Erase one, and the world gets measurably, unavoidably warmer. There is no wall between the ghostly ledger of information and the physical ledger of energy. There never was. It's one book.
And there's a phrase for that, isn't there? You've been circling it all night.
There is. It's Landauer's own, and it became a kind of watchword for everything that came after. 3 words. Information is physical. Not as poetry, not as a slogan on a poster. As bookkeeping. As a line in the ledger of thermodynamics, as real and as binding as the mass of a stone or the heat of a flame. You cannot write down the complete laws of heat, of engines, of the second law itself, without accounting for information, for bits, for memory, for the price of forgetting. It's not sitting above the physics, commenting on it. It's woven right into the physics, load-bearing, holding the deepest law we have together.
That is genuinely one of those facts that reorganizes the furniture in your head. I came in thinking information was the thing computers push around. And you're telling me it's more like it's a substance. It's on the periodic table of what the world is made of, right next to energy.
Right next to energy. That's not a bad way to hold it at all. And now that we've earned that, truly earned it, from the warm patch all the way to the demon's notebook, I get to open the door this whole series was built to walk through. Because if you take information is physical completely seriously, and I mean completely, then a question comes for you that you cannot avoid. The next door.
Go on, I can feel you winding up to it.
Here it is. If information is physical, if it truly lives in the world, obeys the world's laws, pays the world's prices, then it must obey the world's deepest laws. Not just the everyday physics of warm gas and sliding pistons, the real bedrock. And when you go down to the bedrock of physics, down past the molecules, down to the single atom, the single particle of light, the smallest pieces there are, the rules change completely. Down there, the world stops behaving like coins and pistons and trapdoors. Down there, the world is quantum. And that forces the question that names this entire journey. The bit, Shannon's bit, the clean yes or no, the settled coin, that was the atom of ordinary information. So what happens to information when the thing carrying it is a quantum thing? What is the atom of quantum information?
Because a bit is the most decided thing in the world. It's a yes or it's a no. It's heads or it's tails. It's committed. And the quantum world doesn't do committed, does it? That's the whole strange reputation of it.
That's the whole strange reputation of it. And I'm going to leave you sitting right on the edge of that, because it's the first thing we pick up next time, and it would be a crime to spoil it tonight. But feel the shape of the gap. A coin, while it's spinning in the air before it lands, it isn't heads and it isn't tails. We just say that because we can't be bothered to track it. But a quantum thing can be poised between its answers in a way that is not laziness, not us failing to look. It's genuinely how the thing is down at the bottom. So the smallest unit of quantum information is not going to be a tidy little heads or tails. It's going to be a far stranger animal, something that holds more than a bit, and yet, when you finally look, gives you only a bit back. It has a name. We've had the name for a while now.
And you're not going to say it.
I'm not going to say it, because a name handed over before you can feel what it's for is a name you'll only have to unlearn, and I'd rather you earn this one. Tonight, you earned the biggest idea of the whole course, the route the rest of it grows straight out of. Information is not a ghost. It's physical. It has a temperature. It has a price. It holds the second law together, and it's woven into the deepest fabric of what is. And the deepest fabric of what is quantum. So there's a new kind of information waiting down there, obeying strange new rules, and a new kind of machine you might build to handle it. That's the whole road ahead of us.
Information is physical, and physics underneath is quantum. So somewhere down there is quantum information, and I don't even have a picture for what that could be yet.
Not yet. But you have the question now, sharp and true, and a good question is most of the journey. Sit with the warm patch under your hand tonight, the machine forgetting, out loud, paying its tab in heat, and know that the very same idea, the price of a bit, followed all the way down to where the world turns quantum, is about to become the strangest and most powerful thing either of us has ever tried to understand.
The atom of information shrunk down until the quantum takes over. That's where I want to start next time. I came in tonight thinking a warm laptop was just a warm laptop, and you've turned it into a doorway. Good night.